Hello, and welcome to a lecture on duality and magnetic current. Here is the outline of this lecture. First, a quick reminder of what the duality principle is. I'll explain briefly magnetic current. I'll explain radiation problems using the magnetic current, as opposed to the electric current, which we may have covered in a previous lecture. And then a suggested exercise. So first, the duality principle. Every electromagnetic field problem with a valid solution has a dual problem. And we don't necessarily mean a physical problem, but a dual problem with a mathematically valid solution that can be obtained by a simple exchange of notation. When duality is applied, electric current becomes magnetic current. Now, magnetic current's not a physical concept, so this raises some questions. Often the dual problem offers some mathematical or procedural convenience, so this can be very useful even if it is a bit weird. Here's a brief summary of the duality principle as it applies to electromagnetics. On the left, we have the situation as it's commonly understood. In this case, we have not yet introduced magnetic currents, we have only electric currents. When we have electric currents, we will identify the resulting electric field intensity as E sub A, the resulting magnetic field intensity as H sub A. And the subscript A is alluding to the method that we use to compute the electric and magnetic fields. That is, we use the concept of magnetic vector potential, A, as an interim step in computing the fields. So first we integrate the currents to get A, and then we integrate A to get E and H. So here is the current, which is serving as the source. And then what follows is a list of the parameters that appear in these problems and their solutions. The permittivity, the permeability, the wave number, right? That's 2 pi over lambda, has units of radians per meter. The wave impedance, that's the square root of mu over epsilon, has units of ohms. And then the admittance, we can have a wave admittance. It's just a reciprocal of the wave impedance. On the right, we have the dual situation. So in this case, we have no electric current. We have only magnetic current. We obtain the new formulation by a simple exchange of notation. So everywhere we have electric fields, we now have magnetic fields. And simply to identify the fact that these are arising from magnetic currents now, we use the subscript F. What is F? F is the electric vector potential. The electric vector potential. It plays the same role that the magnetic vector potential plays in problems in which we have electric current as a source. When we have magnetic current as the source, we integrate over that magnetic current to get an electric vector potential, which we call F, and now we're identifying the resulting E and H fields with the subscript F to indicate that these are resulting from magnetic current. H in the electric current source scenario becomes minus E in the magnetic current source scenario. So we change H to E and we add a minus sign. J's, of course, become M's. A, the magnetic vector potential, becomes the electric vector potential. We'll say a little bit more about how that's computed later in this lecture. Everywhere we see permittivity, we replace it with permeability. Everywhere we see permeability, we replace it with permittivity. Wave number remains unchanged. There's no exchange of notation there. But interestingly, impedance becomes admittance, and admittance becomes impedance. So here's a summary of the duality principle as it applies to electromagnetics. Now let's examine the Maxwell curl equations from the perspective of duality. So here's Maxwell's curl equations as you have previously encountered them. Simply put, the curl of E is minus j omega mu h. The curl of H is plus j omega epsilon E plus j, and this is where the current source comes in, the electric current source. Now, in duality, we recognize that these two equations are in fact duals of each other. In other words, you can apply the principle of duality to this equation and you get this equation, and vice versa. However, that only works if you introduce the magnetic current here. So we're going to do that. From now on, we'll represent the Maxwell-Faraday equation as having an additional term on the right, minus m, for magnetic current. There's really no problem with doing this in general because in physical problems, we know m is 0. However, in scenarios in which it's useful to invoke the concept of magnetic current, this provides the general formulation. I should also point out that the magnetic current has units of volts per meter squared. Recall, the electric current, J, had units of amps per meter squared. That's a volumetric electric current density. So the volumetric magnetic current density turns out to have units of volts per meter squared. And you can verify that by dimensional analysis. For example, the electric field intensity has units of volts per meter. If you differentiate with respect to spatial variables, you get volts per meter squared. So this again shows that this should have units of volts per meter squared. So, summarizing, the Maxwell curl equations are duals if we insert magnetic currents as shown above, and there's no problem with doing that. No problem to assume this form is general as long as we do not forget that magnetic currents do not exist in practice. It's fine to use them, but we have to remember that when the smoke clears, if we go back to the physical problem, we better not require that the magnetic currents actually be there. We can use magnetic currents to represent other things, and that's where their utility lies. Okay, if we now have magnetic current, we should be able to identify boundary conditions that apply. So let me remind you about the boundary conditions on the electric current density. Here's region 1, here is some surface, here's region 2. We have the normal, as usual, pointing into region 2. We identify some electric current density flowing along the surface. Now note this is now a surface current density, so this whole thing has units of amps per meter because this is a surface current. And the boundary condition that you're hopefully already familiar with is that that surface current should be equal to the normal cross the difference in magnetic field intensity on the surface. Now we introduce the magnetic current. We represent that as being a double-headed arrow. This is a fairly standard way to do this. So if you see a double-headed arrow, that's a pretty good indication that we're talking about magnetic current. The relevant boundary condition we can obtain using the duality principle. And it says simply that the magnetic surface current, now we have units of volts per meter. This is a magnetic surface current. Minus sign, n hat, same normal to the surface, cross the difference in the electric field intensities on the surface. So this is the relevant boundary condition that applies to the magnetic current density. So what are the applications for magnetic currents? From the boundary conditions, magnetic currents can be used to replace the electric field over a surface. You might have encountered this previously as the equivalence theorem. Using this concept, it becomes quite easy to do radiation problems in which we have, for example, apertures and ground screens. So, for example, if we have some screen here, I'm showing it as a sheet of some kind, and maybe we cut a slot into it, and then the slot is somehow illuminated from the bottom, and we ask ourselves what radiates now from the slot, it turns out that this is very easily done using the concept of magnetic currents. And we obtain those magnetic currents using the boundary conditions I just showed you. Also, you may have encountered problems where we have some kind of surface and maybe have a window in the surface. And we can say, or we know something about the electric field in the surface, and we would like to know how that now radiates. A simple way to do that problem turns out to be to replace the electric field with a magnetic current density using the equivalence theorem, or using the boundary conditions I just showed you, and then allow those magnetic currents to radiate. That's a relatively simple way to do the problem. And in later lectures, we will certainly encounter techniques that use that. Apertures in free space is another application. The big one here that you might imagine is horns. So here's my crude picture of a horn. The horn has some aperture here. It turns out to be relatively simple to at least approximately estimate the electric field over this surface at the opening of the horn. And then we can play the same trick. We can convert the electric field in this surface to a magnetic current density, to a surface magnetic current, and then let that magnetic current radiate, thereby allowing us to compute the electric and magnetic fields that the horn radiates. A third application is phased arrays. So here's my very crude picture of a planar rectangular phased array. Of course, it would consist of many elements in this aperture, but we can in general represent this whole arrangement of antennas as a magnetic current distribution and then allow that to radiate. In fact, in general, and we may see examples of this in later lectures, we can represent this as a combination of electric and magnetic currents. So this turns out to be a very powerful and simple way to analyze phased arrays. This is also commonly used in feed models. For example, here's a sheet. We may have a monopole sticking out of this sheet, and the monopole emerges from a hole. So one way to represent the feed part of the monopole is to replace this section here with this thing that's known as a monopole frill current. And that frill current turns out to be best represented as a magnetic current. Another way this emerges is in the form of a thing called a Huygens source. Huygens sources will be a topic of another lecture, but I will simply tell you now that they turn out to be very useful. They consist of an electric current moment co-located with a magnetic current moment, and it gives us a very powerful way to model a broad class of antennas. Superposition. Superposition allows us to decompose any problem into two simpler problems, recognizing now that problems might have electric currents in them and magnetic currents in them, for the reasons I described in previous slides. One way to attack these problems is to first do the electric currents alone and represent that using our notation that we've established already. These give rise to a set of fields, E sub A and H sub A. And then we can do the problem using just the magnetic currents alone, and thereby getting another set of fields, E sub F and H sub F. And then, of course, the solution to the original problem is the sum of those things. So we add up the fields resulting from the electric current to the fields resulting from the magnetic current, and that's the total solution. And this is just nothing more than an expression of superposition. Let me remind you very briefly of how we do the solution for radiating surface currents. So here's a very general picture of a geometry where we have a current around some volume. Here's the field point. And we know we can find the electromagnetic fields resulting from those currents by first integrating over the surface current, right? This has units of amps per meter. This has units of meters squared. So collectively, these two things are a current moment, having units of amps times meters. And then we do the usual thing. We multiply it by some phase function divided by some magnitude function, integrate, multiply by mu over 4 pi, and that gives us the magnetic vector potential. So in summary, we get magnetic vector potential by integration over the currents. We get H from the defining relationship for the magnetic vector potential, and we get E from one of the Maxwell's curl equations. For radiating surface M's, the solution is actually quite simple. All we have to do is apply duality. So now when we have m's out here, the problem goes like this. We take the magnetic surface currents, which have units of volts per meter, and over here we have the differential surface element, has units of meters squared. So collectively, this thing gives us a magnetic current moment having units of volts times meters. And the process is exactly the same from there. Phase function divided by magnitude function. We integrate over that whole thing. Epsilon divided by 4 pi obtained from duality. This gives us the electric vector potential. Now what? Let me erase some things to make this clear. Now to get the electric fields resulting from those magnetic currents, we apply the defining relationship for the electric vector potential, which we obtained from duality. So the electric field is simply minus 1 over epsilon curl of the electric vector potential. And then we get H from Maxwell's equations. Remember, the Maxwell's curl equations are duals of each other. So we could think of this as the dual of the associated equation in the previous slide, or we can just think of it as the other curl equation of Maxwell. Okay, now let me just draw out the universe of possibilities here for electric current. And the point is now I want to bring in far field computation. So in general, when we have electric current, we can compute the magnetic vector potential. From that, we get the magnetic field. From that, we get the electric field. But we know that if we can go into the far field, right? If we know the far field conditions apply, then it becomes much simpler to get the magnetic vector potential. It's now reduced to this relatively simple integrand, and we multiply the result by a spherical wave, removing the radial component of the magnetic vector potential and multiplying by minus j omega. And we can get H from the plane wave relationship, right? This is just assuming that we have a plane wave in the far field and applying the appropriate relationship. We can do the same thing with M, with the magnetic current. Again, the general way is to integrate over M to get F, the electric vector potential, get the electric field from the electric vector potential using this curl equation, and getting H from E using a Maxwell's equation. So now if we know that the far field conditions apply, we can do this. We get a simpler expression for the electric vector potential in the sense that the integrand is simplified and we multiply the result by a spherical wave function. H we get simply by removing the radial component of the electric vector potential and multiplying by minus j omega. Again, we could obtain this by duality from the associated expression on the previous slide. And then E we get by assuming the plane wave relationship, which applies in the far field. This is the locally planar approximation, and we simply apply that plane wave relationship. I'll also note that frequently we just want E. We don't always want both H and E. So if you want to get E directly, a quicker way to do this is simply to get F and then invoke this expression, j omega eta r hat cross F. That's a quicker way to get the electric field in this case. So now an exercise. This is intended to give you some experience in coordinate-free notation, which is useful for a number of problems that we may encounter in other lectures. This is a problem which I have probably assigned in some previous lecture, and basically all it asks for is you have an electric current filament located at the origin. It's probably electrically short, and then you come up with expressions, and you find out that you can come up with electric and magnetic fields in those forms. These are the coordinate-free expressions. See, nowhere in here do we have x's, y's, or z's. Now, knowing what you know about magnetic currents, you can use duality to obtain the associated expressions for the case in which you have not an electric current filament, but rather a magnetic current filament. So that's the problem. Take what you know about this and apply duality and get the associated expressions for the magnetic current filament. This concludes this lecture on duality and magnetic current.